Our example now gives us a partially known state of stress. We're told that sigma x has a plus 5 megapascal value. Again, positive is tension. Sigma z is equal to 0. And sigma y is unknown. That's what we're actually going to solve for. That you know that the strain in the x direction is given as that value. And so what we'd like to do is solve for sigma y. And we're also given Young's modulus of 5 gigapascals. So we want to stay on top of this units wise. We've got megapascals and gigapascals that we're going to have to reconcile. So let's look at how we're going to approach this problem. Given that we know a strain, I'm going to go ahead and write out Hooke's law. 3D Hooke's law for strain in the x direction, which is going to be a function of all the 3 normal stresses, sigma x, y, and z. So this is what we want right there, sigma y, y. So let's just go ahead and take a pretty good accounting of what it is we know and don't know about this problem. So E, Young's modulus, 5 gigapascals. I'm going to convert that to megapascals because we're going to take the stress and divide by E. So we have consistent units now. Sigma x is just written from above is plus 5. Sigma z is 0. Sigma yy is what we're going to solve for. And epsilon x is given to us as a positive number. So we're actually all set from an unknown and known point of view. We've got one equation right here, and that'll be our only unknown. We know both the other stresses. We know E. We know Poisson's ratio of 0.3. And so we also know epsilon xx. So we're going to use this one equation to solve for our unknown. So taking us through here, this is 0, right? Sigma zz is 0. So let's go ahead and multiply E out. And so we end up with epsilon xx times E. We'll go ahead and start isolating sigma yy. We'll take sigma xx to the other side. Reshuffle. Go ahead and divide by negative Poisson's ratio. And so our signage works out to sigma yy is equal to the expression shown right there. Right? Again, this is true because sigma zz was equal to 0. So we're actually just ready to plug in our values. So we'll do that. Go ahead and plug in your values, do your multiplication. All of our units are consistent. So we end up with a negative value, which means it's in compression. So part B of the problem asks for us to take that answer, which we just found for sigma yy equal to 2 megapascals in compression, and use it to solve for the strain in the y direction. So we're going to work our way through 3D Hooke's law. So the strain in the y direction is composed of the direct stress, so sigma yy over E, and then Poisson's ratio with sigma x and sigma z. So we just plug in what we know. Sigma zz is equal to 0. We'll go ahead and just simplify our expression just a little bit. Help us out math-wise. So epsilon yy. And then all we have to do is plug in the values that we have using our newly found answer for sigma yy. So plugging in, end up with an answer minus 700 times 10 to the minus 6, or minus 700 microns would be how this is also expressed. So just as a little bonus here, why don't we just tie this all together back to the stress block. And so we'll put some coordinates on here. We'll call that x, y, and z. So what do we know about our state of stress? In the x direction, it was 5 megapascals. So again, that stress would also be on the back face, back here. That would be 5. In the z face, right here, we've got no stress, right? Sigma zz was equal to 0. On the y face, we've got 2 megapascals of compression. So that would be 2 megapascals. So there's our state of stress if we wanted to draw it on a stress block.